are pleased today to welcome Professor Chazelle as a guest and friend at Birzeit University. Professor Chazelle, he born and grew up in France. He got his bachelor's and master's degree in applied mathematics, and then got a PhD in computer science at Yale University. For now, he's a computer scientist at the computer science department at Princeton University. He also has different interests in politics. He wrote articles in like Bush's desolate empire. He also wrote another article in anti-Americanism, and now he will give a talk in computer science entitled, our title is "What Are Natural Algorithms?"
Well, thank you very much, and thanks everybody for being here. I was here 3 years ago, and I always wanted to come back, and I'll be back again, I'm sure. Now you see it's so dark in here that I cannot see the time it is. So I may talk for 3 hours, so somebody's going to have to stop me at some point, okay?
One hour is enough?
1 hour, yeah, okay. Sure. Yeah, no, if I go past 1 hour, please. Yeah, maybe some light in the back, yeah. Yeah, so let me just start with, so I don't really know your background. I guess you're a computer scientist or something. And I'm trying to give a very high-level talk, but there will be some moments where things are maybe technical. I won't define all the terms, but it's okay. Just take it as it comes. The 20th century is remarkable for the power of mathematics. Pretty much everything around you can be described, or 99% of things around you can be described by filling 1 page worth of mathematics and explain everything that you have. Now, Eugene Wigner, a famous physicist, said that the unreasonable effectiveness of mathematics in the physical sciences is what explains this phenomenon. But actually, that's not what he said. He said the unreasonable effectiveness of mathematics in the natural sciences. And that's more debatable, okay? It's certainly true for physics, but I'm not so sure that in biology, mathematics would be nearly as important. It would be important, but maybe not nearly as important. So, you can ask whether biology, the new sciences of the 21st century, whether it's brain science or science of networks or the social sciences, will also lend themselves to equations, with the sciences of the equation. So people say no, they will not be. There will be sciences of the computer. That's what you do everywhere. I actually don't believe that myself. The computer will be indispensable. But I don't think there will be. I think there will be the sciences of the algorithm. And that's the topic of my talk. But to justify this. Equations, and I use the word equations in a very broad sense, referring to mathematics. Equations and algorithms both tell mathematical stories. So they're in common. The difference is the kind of stories they tell. Equations tell stories about symmetry, and physical science is still symmetry. But algorithms tell stories about complexity, which is a different thing. So you can ask, well, what is complexity? And often if you went to the previous talk, I said, hey, you idea of complexity as fractals, beautiful pictures like this, and some people call complexity just that. But I want to use a different understanding of complexity. Well, I'm going to refer to this. This will represent complexity actually in 2 ways. First, there's the leaf, and then there is the ants themselves. I'll give you some other examples. This represents complexity. Cars and traffic and people doing their own thing and having patterns, having goals, and cooperating. This represents complexity. So it's very different from what you see in the physical sciences. But that's what I will define as complexity. And this, I love this picture, I mean this video. So what we have here, this is a scene that takes place near Oxford in England. And there are very few places in the world where you see this. So these are birds, these are starlings, kind of birds. There are lots of them. Total, there's about 500,000 birds. And around 7 p.m. at night, they come together and they do this ballet for reasons nobody really understands. So there are theories why they do that. See, after they're done with this, they go and sleep on their roots. So they just go to trees and just sleep there. It's not clear why they bother doing this. Some people think, well, they're warming up. Other things, they're courting, it's a sort of sexual thing. And others things are competing for the best trees. Who's going to sleep in the best bed or something like that? Who knows? Nobody really knows. And what's remarkable is this, is that, you know, a bird is not a terribly smart thing, but, you know, when you teach discrete mathematics, introduction, there's this paradox, birthday paradox theorem, that would say that it will be inevitable that you will have collisions, that at least two of these guys will collide at some point. And no one has ever witnessed two birds colliding. There are 500,000 of them. Never two have ever been witnessed colliding. So how do they do it? This seems to defy all sorts of basic laws that you understand about nature. So complexity in that context is very different from the fractal picture I showed. First, there's this notion of autonomous agents, whether birds or fish or drivers. They're independent agents and they have their own goals, their own way of doing things. And they have the ability to communicate somehow. They can visually or by whatever means, they communicate with others. And another aspect, which is not necessary, but which is often the case, is heterogeneous, which means that you don't have, they're not all the same. You could have the birds, you could have predators and prey. You could have different species, you could have different kind of particles, you could have different kind of things competing in some. So in biology, this concept occurs everywhere in biology. In fact, it occurs in all the natural sciences. You cannot name a single natural science where you don't have something like this. And I want to argue that equations do not have the expressive power to handle such things, and only algorithms do. Not just that algorithms do, I believe only algorithms do, simply from a linguistic point of view. They have the expressive power to model what's going on. Well, you might ask, what's an algorithm? Of course you know what's an algorithm. You're studying computer science, or researching, teaching computer science. So I assume you know what an algorithm is. But the point I want to make is here I will distinguish between two kinds of algorithms. The classical kind, like multiplying numbers, sorting, searching, Google, or the natural kind. So this is a classical algorithm. It's a data compression algorithm. You don't have to know what it does, but it's represented in a typical flowchart fashion. There are other ways of representing the algorithm, but that's one. So you don't have to know what this does, but this is an algorithm. It's a classical in the sense it was discovered, it was invented by human beings. Okay, this is a natural algorithm. This is the algorithm for protein P53. It's a protein which plays a huge role in your body because it prevents you from getting cancer. When this protein malfunctions, then that's when you get cancer. And so of course there's been a lot of study about that protein. And this is what biologists come up with. You don't even have to know what this does. My point is this, you look at the uncanny resemblance between this and that. They do totally different things, but they are both algorithms. This is a very important point. And the difference is this is engineered by humans. This is like a car or a bridge. This is like a star because this is engineered by God. We don't get to decide the human body, we get to draw this diagram. But this algorithm is natural, it comes from nature. But yet, it is an algorithm. This is a very important point. It is no different really from this, in that sense. But there are differences that I want to point out. why in many ways natural algorithms are much more exciting than classical ones. Maybe one of the most exciting classical algorithm is PageRank, which is the Google search engine. You all use it and like it, I'm sure. It works very well. Now, and another one is bird flocking. So there are birds, the agents, and they flock together. Some examples of natural algorithms. Now this one took about 100 years, took no more than 100 human beings to design it, and over a period of at most 10 years. This one took over 1,000 trillion designers, over 100 million years. Now birds are not very smart. We are smarter than birds, I understand that. But we have to compensate. I mean, the ratio 100 over 1,000 trillion in 10 years versus 100 million years. So my point is that it's not surprising that this algorithm is infinitely more clever than this one, simply because so many agents have tried so hard to make it better. Okay? And the price of failure in nature is death. So the stakes are very high. It's not just a promotion in your company. It's very serious. So natural selection is the ultimate software designer, and that's why natural algorithms are so impressive. They're like gold mines. Okay. Now there are only two issues with that. The first one is, well, if it's an algorithm, there has to be code somewhere. There has to be a description. Now, where is that? Now, okay, bird flocking, that's a nice algorithm. Where's the code? How do I know that? So that's what scientists will have to do, not computer scientists, but zoologists, biologists. They'll tell us. That's what they study. What's the algorithm for this? Well, once you have the algorithm, that's not enough. Now you have to study it and be able to make predictions. Okay? So what are the analytical tools that we have to analyze these algorithms? Just like if I give you an equation E equals mc squared or F equals ma, that's not enough. You need to be able to use it. And for that, you need more mathematics. So what are we going to use for this? Now, those of you who went to the previous talk recognize Poincaré and Boltzmann. So there are tools that have been evolved over the years. One from mathematics, the whole study of dynamical systems, that's Poincaré, and a German one, Boltzmann, who studies statistical physics. And these give you all kinds of tools, very powerful tools, to study natural algorithms. But I drew one here, it's very small. This is Alan Turing, the founding father of computer science and the inventor of the computer. And there's a field called algorithmics, and it's very small right now. It does not compare with the others, but it's my prediction that this will come to be at least as big and probably even bigger than the other fields in the future if people do it the right way. So that's what I want to argue. Just as one studies mathematics with mathematics, a lot of mathematics is self-aimed. It's very important to understand that mathematics is one of the only fields with philosophy, first of all, that studies itself. It is itself its own subject. And number two, the tools it uses are part of its study. Okay? That is not true of most other fields. Electrical engineering, the tools are like mathematics and manufacturing. These are not part of electrical engineering. So one studies natural algorithms with algorithms. And this is something I don't think anybody has yet done systematically. That to study natural algorithms, mathematics will not be enough, and computers will not be enough. We'll actually use algorithms. And I want to give you some examples from my work of this phenomenon by looking at some natural algorithms that I've looked at. The first one is bird flocking. So that has been heavily studied by many people. And there's a standard model due to Vishek, a physicist, Cooker, and Smale, who were two mathematicians. And they went like this. So, well, you know, birds are flying, and a simple approximation he says is that every bird will look around a certain radius, and then will draw these edges, and these edges of influence. Tells you that this bird is influenced at this moment by this one, and that. And now what will happen next is that this bird velocity will become the average of these velocities. So if you're this bird and you're flying, you look around your neighbors and you try to adjust where you're flying to reflect your friends. Okay, that's a typical thing that birds do. So you update that. And every bird does the same thing. Okay, so you have a network that comes out of this. It's a temporal communication network. First of all, it's a network, it's a graph. Second, it's communication. It's important to view these as communications. The birds talk to each other. They don't talk with words, but they look, they senses what goes around. It's temporal in the sense that it changes. It's not like the internet, which changes sometimes but not that quickly. This changes very quickly all the time. It constantly changes. So the result that I got showed this, that birds will fly and then they will fragment for a while. And then at some point they will start merging into flocks. And then these flocks will then fly away in steady state. Okay? And the timeline goes like this, fragmentation period, and then there'll be a merge phase, and then they will reach steady state. And the times it takes are astronomical. These are worst case values, of course, in reality it's much faster. However, the model tells you that this is actually optimal. Now there's some tools in there to prove this, and I will not get into the details of these tools. But some of these tools involve algorithms, and that's my point. That to prove these things, you need to design algorithms. So I'll show you one of them. Now, the natural algorithm is birds flying and flocking. It's called flocking. That's the natural algorithm. But now to study it, I will introduce another algorithm. Just like in mathematics, there are things like matrices. And to study matrices, we invent other mathematical objects like determinants. Determinants were invented in order to study matrices. This is mathematics invented to study mathematics. Just like here, well, in order to study natural algorithms, we will invent algorithms. So this is a Birzeit algorithm. So let me describe what the algorithm is. But again, it's an overview, so I don't. This is not a lecture where I teach you how to do this. So it's not going to make any sense. But that's the whole point. You just get the idea. Imagine that there's one baton, and at any time one bird holds it. Now don't ask me how the bird holds the baton. It holds it. And at any time it can pass it to a neighbor, so either to this one, or it can pass it to that one. It has a choice. You can do one or the other. And then at the next step, the baton is here, it can go here or it can go there. And you can do whatever you want. So, but a baton passing algorithm, which is not the same thing as flocking, a baton passing algorithm is an algorithm which is a protocol which tells you how you want the birds to pass the baton that follow these rules. There are many possibilities, okay? And an algorithm will be a specific set of rules which tells you the way you want the baton. And the reason you're going to be designing such an algorithm is in order to prove something, okay? And the result is this, that there exists a baton passing algorithm that keeps the baton almost in a straight line. Now this should be surprising because the birds themselves might be flying in very zigzaggy fashion. They don't have to go in a straight line. They can fly in a very chaotic way. However, what this says is that it's possible for, even though the birds go in all kinds of very complicated trajectories, it's possible for them to hold the baton and pass it to somebody else and pass it to somebody else. So if you just look at the baton, it almost goes in a straight line, almost, okay? Now this is very surprising, and this gives you a very powerful line of attack on this. It says, for example, that after a while, at time t, that if two birds fly with an angle that is at least log t over t, constant factor, and t is large enough, then these two birds will never get back into a common flock. See, this is the sort of statement you have to be able to make to predict when the flocks are going to reach steady state, is to say that if there's a flock here and a flock there and they're flying in opposite direction, I need to be able to say at some point these birds will never get back together. Because otherwise, if I cannot make such a statement, I'll never be able to predict when things will stabilize, because I just never know. So this allows you to make this kind of prediction. Okay. So what happened is we designed an algorithm to study another algorithm, and that allowed us to make predictions. The second example that I use is this. So this is a standard experiment that anybody knows. I don't know, take physics 101 or something. Very often they will show this experiment. So you have 3 metronomes, and they're on Coke bottles of wood, and this is the wood also. This is important. And they have the same frequency, so they have the same timing, but they don't have the same phase. They started in kind of random fashion. And it looked random for a while, but if you wait, the metronomes will start being in sync. They'll start being completely together. So the question is, why? How do they know? The metronomes got together completely in sync. How did that happen? If you repeat the experiment by, instead of having cans of Coke on the table, but you hold the cans of Coke, it will not work. So the metronomes will never get in synchronization. It's very important that it rests on something solid, like a wooden table. Why? Because that's how they talk. The metronomes talk to each other. Okay? And to talk, they need a medium. And the medium is this. So when I say talking, I really mean talking. They're actually talking to each other. They vibrate, and the vibrations are propagated, and they go back to the other ones. Just like when you hear my voice, it's vibrations of the air that gets to your ears. It's exactly the same thing. It's really talking. And they have a language, because it's the language of synchronization. But these signals somehow don't produce a giant jumble, but they convince all the metronomes to start doing things together. And this is natural for any group of, that's why when you have armies of soldiers, when they walk, naturally they will walk in lockstep. So when you cross a bridge, you have to tell them not to do that, because that would create resonance and might collapse the bridge. So we'd like to know why. How is that working? But this is very interesting, but this is very simple. The communication network where they talk is very simple. It's fixed, it never changes over time. It has only 3 notes, the 3 metronomes. Now you can have a more complicated one. So this is a composer. He's dead now, but a famous modern music composer from Hungary who composed a piece of music that's called the Poem Symphonicus, a poem for 100 metronomes. These are metronomes, and there are 100 of them. So it's the same idea, except there's 100 of them, and he starts them in very special ways. But eventually, they all beat at the same time. So that's more complicated, and yet it's still very simple, because the network is more complex, but it's fixed. The network does not change. Whereas the birds, when they're flying, the network itself was constantly changing. Okay? Now here's something where the network changes. So these are, this is a phenomenon which happens very rarely on the planet. There are only a few places, like Malaysia, Thailand, where this happens. Along river side, you see fireflies, like crickets, fireflies. And there are millions of them. And they will cover miles long. So it's not like you see fireflies in a corner. They will just cover a huge area, and they talk to each other. And they will. So this picture is not so good. But what happens is that at first they flash, they slide at random intervals. But after a while, they all flash together, and this will occur over many months. This is phenomenal. And so we want to know why. how do they do it? How do they know how to flash at the same time? Fireflies are not very smart. The brain is really tiny. And in fact, you don't have to be smart. This is done by mechanical objects like metronomes. It's done by power stations. Like power stations have electricity at a certain voltage, and they communicate. And they always do. And they have to be in synchrony, otherwise it creates fires and explosions. And the same phenomenon happens. So you see, your heart has 10,000 cells that have to beat at the same time. And the reason they beat at the same time is because of these principles. It's extremely general. And as in flocking, the communication network is temporal. And this always converges. And again, I studied the speed at which this happens, but I actually proved something much more general that I want to tell you about. So this is going to get a bit more technical, but I guess this is fine. Now these are called bidirectional agreement systems. The word bidirectional refers to the fact that if I'm able to communicate, with Adnan this moment, then he can do the same with me. The graphs are undirected. Okay, this is the assumption right now, like you make. We will relax the assumption later. So consider an arbitrary sequence of graphs with n nodes. And the first graph is, so these graphs are embedded in space. Just think of this as the fireflies in 3 dimensions. And so each firefly is a node of the graph. And there's an edge if they talk to each other. And so the way it starts is it's an arbitrary embedding. We make no assumption of where the fireflies are when they start. But now here's the first graph. That's where they talk. And here's what we do. This is one firefly, one node. We look at the neighbors, and then we take the complex hull of that, and then we shrink it just a tiny bit. Okay? And then we move this anywhere. Okay? So we move this anywhere. Okay, so this is much more general. This is much more general model, and you do this for everybody. So you can have this. This is the first step. Then the graph changes. But the new graph is arbitrary. It can be anything you want. And then you do it again. And the motion is also arbitrary. Okay? So this is so general that with this you can model everything that I talked about earlier. So general. You can actually model fireflies, metronomes, all of that. And I don't tell you why, but trust me. And so on. And this goes on and on forever. And here's, so remember, it's incredibly non-deterministic, extremely general. Any graph sequence you want, any initial embedding, and any moves within the perturbed complexes. And what I showed is that this will always converge, no matter what. This is quite surprising. So this thing will just go like this. It might take a long time, but eventually it will converge. And now by converging, those things don't freeze. They keep getting closer and closer and closer. So the system always moves. But my point is for any epsilon, if you wait long enough, everybody will be within radii epsilon of each other. Okay? Now I don't know if you know much about random walks, but that's something that we study in computer science, in particular for Google search engine. But if you think dually, then what we're really doing is equivalent to doing random walks over graphs that change all the time now. The way people talk about Markov chains and random walks, they think there's a fixed graph, and then you hop around at random, and you do a random walk. But the graph is fixed. Now here, we're doing the same thing, hopping randomly from node to node. But the difference is that every time the graph changes. Okay? And we want to make stiffness out of that. The reason this is important to know is that if you've never seen this problem before and you try to prove things about it, you should be aware of this because it means that your theory will have to contain all of Markov chain theory, de facto, because your model is more general. And so whenever you make a statement by convergence, this will apply to any Markov chain. So it might not be so simple. So this leads to the total S energy, which is a new device invented for this purpose, which goes like this. So you take a graph, and I want to measure how this thing evolves in maybe convergence. So here's what I do. For each edge, so these are in space. Think of the fireflies in 3 dimensions. So these are in space, and each edge therefore has a length. And so I look at the length, and I raise this to the s power, where s is a variable, okay? S is a variable. And then I sum this over all possible times. Now, I don't think anybody before looked at this sum for the simple reason, which is these should never converge. I mean, these are all positive numbers. You sum to infinity. Why should this thing ever converge? I mean, these could be big numbers. So this sounds completely absurd. And sure enough, for example, if you set s to be 0, then you get infinity. In fact, why shouldn't that be infinity for all s? In which case, this would be useless. But there's something surprising, actually, show that this is not infinity. That, in fact, you can do very big bounds. But for this, and in particular, this bound is optimal. This bound is probably not optimal. But this bound is optimal for s equals 1. Now, s represents the temperature of the system. Right now, it's not clear maybe why. But maybe later on, we have some time. I can explain to you why this corresponds to the temperature. Yeah, check the time, because I don't know how much time I have left. Now, if you can prove this, then for reasons that are technical, I don't think we find too interesting. Now, from this, you can imply convergence and balance on convergence time. So now I can tell you how long you have to wait for the crickets to eat in sync, to flash in sync, or for the metronomes to start being together. And that is because this is a generating function. It's a very powerful object from which I can extract lots of information. Now, pursuing the Markov chain analogy, so I don't know, maybe I'm talking just to the subset. I don't know how many of you know about Markov chain, but there's a particular kind of Markov chain that's very useful called reversible. And reversible Markov chains means that when you see evolved, or let's say you see evolve, and then somebody makes a video, and then plays the video either forward or backwards. And if you look at it, you won't be able to tell which is forward and which is backwards, because they look the same. So that's reversibility. And reversible chains converge fast. That's what's important. And so, is there such a thing as a reversible agreement system? So agreement system is the name we give this dynamical system that I described. It's a system because it's a dynamical system. It's called agreement because all these agents, in some strange way, are trying to reach some agreement. See, by moving inside the convex hull of your neighbors, you try to, you're subject to the influence of your neighbors, and you're going to move somewhere toward the center. So that's what agreement means. So yes, in fact, one can define the notion of reversibility, and then one can also prove this theorem. Now this will imply, as a subcase, the standard result of a reversible Markov chain. And what's remarkable about this, and this is and what's remarkable about this is that it's so much faster. The energy here is polynomial in n, whereas here this is exponential. Rho is less than 1, so this is bigger than 1, and there's n squared here. So this is heavily exponential, but this is polynomial. And so there's a huge difference between polynomial and exponential. And that's the same difference we see when we take a random walk on a graph. And if the graph is reversible Markov chain, for example, if the graph is undirected, then this will converge in polynomial time. But if the graph is directed, then this is not reversible, and typically it will take exponential time to converge to mix. Now, the total S energy, so this is for the mathematicians among you. The total S energy is a generating function. Okay? I guess generating functions are not so popular in pure science, when I was a grad student, they were very popular because Donald Knuth had published on these volumes, and he was one of the big promoters of generating functions to understand the behavior of algorithms. And they encode all kinds of complicated things into one convenient object, mathematical object, which can be looked at in two ways. It can be looked at as an encoding of numbers and having combinatorial properties, but it can also be looked at as an analytical object that you can treat with calculus. You have derivatives and things like that. Now, the total S energy is quite complex because, for example, in the case of a graph with only two nodes, okay, only one edge, and it's not even temporal, it's fixed. That super simple case, and in length of 1 over k and time k, that will, the total S energy of that is this function, which is called a Riemann-Zeta function. And the behavior of this is the biggest open problem in mathematics today. It's known as Riemann's hypothesis. And so just to say that even something simple like this can be extremely complicated. So one should not raise our hopes that we'll be able to understand this object completely. However, it's nice to know that total S energy encodes everything. Now you see, not only it encodes everything, but because it has an inverse formula, it truly is a generating function. And a generating function not only encodes all these numbers, all these lengths, but it's reversible in the sense that if you have the length, you can produce the function E of S. But if you have E of S, you can go back and produce each of the length. In other words, there's no loss. There's no information loss. This encodes everything. Okay? And then one can make statements about such objects. We like to think of them, what happens when S is a complex numbers. That's the sort of thing mathematicians do for all kinds of reasons. And then you can make statements about this. Let me just skip that. But why is this object useful? People ask. And well, the intuition, I'm not giving the intuition for why it's useful. Another way of looking at everything I'm doing, which is equivalent, but it's not very helpful. That's why I'm doing it. And is as a product of stochastic matrices. So you know what a matrix is. And when a matrix has the property that all the elements are not negative, and each row sums up to 1, each row is a probability distribution. And the whole thing is called stochastic matrix. And stochastic matrices are used to model random noise precisely. And so you look at products of animals like this, and typically it's very hard to make statements about such objects, unless the matrices are all the same. If the matrices are all the same, then it's like p to the kth power, and that's easy to make statements. But otherwise, it's very difficult. However, you can look at it geometrically. If you look at this matrix, okay, just one, and you look at the first row, and you can look at this as a point in R4, because this has 4 coordinates. So this is a point in 4 dimensions. And you can do the same thing for each row. So you get 4. And now take the complex halves. So this is this. You give me a stochastic matrix, and I give you now you can do this in any dimension. And so this way, given a stochastic matrix, you associate polygon or polytope in general. Okay, so given a matrix like this, now suppose this is big, it's n by n. It's not just 4 by 4. Then you get a complex polytope. And then you have P2, you have another complex polytope. Now you can ask, well, when I multiply P1 by P2, it's like multiplying these two polytopes. Well, what does that mean? What do I get? So you can do the math and see that if P2, if this is the polytope that's associated with this, it's smaller. In fact, it will fit inside P1. Always fits inside P1. What this means is that if you start with P1 and you multiply it by P2 and by P3 and so on, then these get smaller and smaller and smaller and smaller. It's like a nesting thing. And virtually every result on products of stochastic matrices tries to assess how quickly it shrinks. Does it shrink slowly or quickly? And the way it does it, there are many ways it can do it. Look at eigenvalues or other measures, but it only looks at it locally. It it tries to say, well, the movement goes from here to here is fast because the volume goes down by a factor of 2. So then this statement holds here, this statement holds there, and so on. But this is a very strong statement because it could be that this thing shrinks over time, but there will be long stretches where there's virtually no shrinking. So this is trying to do too much. The S energy is very different. It makes a statement, there's an extra parameter there, the temperature, and it tries to make this statement that's global. It tells you how this evolves over infinity, over infinite amount of time. And you can take the temperature as you like it. This is a statement for any S. And once you have that statement, then you can take your favorite S and plug that in. That's what generating functions do. So you have a global quantity instead of the local. Now here's the thing, the proof itself, why this is true. With the earlier bound I gave you on the function, the proof itself, again, is an algorithm. The proof is an algorithm. So this is very, I really insist on this concept because I don't think people like to think of proofs being themselves algorithms. Here's the way it works. So there's an old technique very familiar to people who work in algorithms and data structures that was pioneered mostly by Bob Tarjan and Dennis Slater and many others, which is the sort of credit amortization techniques to analyze algorithms. And one way of thinking about it is like this, that these are the agents, and they're going to be moving over time. And what we're going to do is give money, associate a piggy bank with each agent, and a certain amount of money in there. Okay, a certain amount of money. And then, when this moves, we're going to use money from this piggy bank to pay for the cost. So think of this as paying for gasoline. So you're going to be driving here, and you have enough money to pay for gasoline. But here's the problem. Usually you don't have enough money. Either you have too much money, or you don't have enough. So the whole system is to create an economy by which other agents can borrow or steal money from others who have too much. So to do that, we will have a bank. And what will happen is, as these particles move along the trajectories, they will be paying for gasoline out of their own piggy bank. But sometimes they will not have enough money. So they will borrow money from the bank, which they will never pay back, usually. Or they have too much money, in which case they will deposit the money in the bank. So the banks will get two kinds of requests. There will be deposits and there will be requests for money. And initially, each piggy bank has a certain amount of money that's determined by the position, by the initial position. And now, the algorithm is what? Well, the algorithm is this whole banking, this whole economy that says, I will tell you how much money you should put in the bank when. So I see how much money you have in here, I see how much you're driving, and I will tell you, the algorithm will tell that agent, now it's time to put some money in here, and here's how much you should put. Or you'll say, now it's time to withdraw money from the bank and use it for your own things. So think of a very wise person controlling the economy, maybe like your finance minister, and telling you, now you should put money in the bank, you should withdraw this much from the bank, and so on. Now, if the minister knows what he's doing, then the bank will never go bankrupt. And if you follow the events in the United States in the last few years, you see that this algorithm has not worked at all, because most of the banks have gone bankrupt. But for this algorithm to work, this algorithm has to ensure that at the end, everybody pays for their own travel with the money they have in the piggy bank. And the big bank never goes bankrupt. And money is never used twice. I mean, no, it can be used twice, but it's never duplicated. The total amount of money in the system never increases. It's no more than what it is at the beginning. Okay. So if you can specify such an algorithm, then you'll be able to account for how long these trajectories will go. And then in turn, for reasons I'm not telling you about, but that are plausible, then you can bound the S energy. Okay? So again, this is an algorithm. Third application I want to talk about is opinion dynamics. So this is a very famous classical model of opinion dynamics, probably the most studied, called the Hexelmann-Krauser's German model, which goes like this. So think of yourself on a political spectrum, and there's, maybe there's the left and the right. And you're not, I don't know where you are, but let's say you're somewhere, and your opinion will evolve over time. And the way it evolves is the following. You will listen and you will talk to people. And they will influence you, and you will influence them. However, there's a twist. And the twist that sociologists have decided is the right one. And the twist says that you're only influenced by people you trust. So, you listen to Netanyahu, I don't think you are influenced by what he says. Even though you may listen to him all the time. So just listening to somebody does not mean anything. Because you might be listening to it and just shrug your shoulders, and that doesn't change your opinion at all. On the other hand, if you talk to a good friend of yours that you trust, who has a different opinion, but not too different maybe, but somewhat different opinion, that might influence your judgment. Because it's somebody you trust, and it's somebody whose opinion is not that different. So you might actually make a move toward. Now, what if you have several friends that you trust, and they have diverging opinions? So this friend wants to influence you this way, and that friend influences you that way. Then what happens? Maybe they cancel each other. So this is the kind of model that those people have studied. So, in other words, in the simplest version, you rank your opinion between 0 and 1. So maybe 0 means you're super left wing, and 1 you're super right. And then there's a number that tells you where you are. So everybody has a number. This is you. So here's what you do. This is your window of influence. You will decide how much you're influenceable. And if you're the type who is easily influenced, then this number will be very big. It says you go 0.1 to the right, 0.1 to the left, and everybody here will influence you. If you are extreme, if you're very stubborn, you never change your mind, this window will be tiny, tiny, tiny. But if you're very easily swayed by what you hear, this window will be very large, very big. Everybody will influence you. So it depends on your own personality what this window is. But everybody has a window. And what they do is you listen to their opinion. So here it's this one, it's yourself. You always listen to yourself. Okay. So you listen to yourself. You listen to this person, to that person, maybe this one, and then you take some kind of convex combination. Let's say the average. You take the average and you move to the average. Okay. You move to the mass center of your neighbors, which represent this influence. Okay. So if you have two neighbors and they're equally distant from you, they cancel each other, and you don't. Right? And everybody does the same thing. So they all do that. Okay? That's one step. And then they repeat. And they repeat. And they repeat forever. And the question is, so this is things that political scientists want to know. Or people, these are political opinions, but you can also apply this for people who drink Coca-Cola versus Pepsi. And if you're trying to sell Pepsi-Cola, then you want to understand how this works. So in particular, you want to know whether the system is polarized or consensual. Do people eventually, if you wait long enough, agree? So they're all together at one point, or do they fall into camps? Okay, and each camp maybe agrees. And so, for example, this is an experiment. And this is a simulation of this, where you have 100 agents, and they're random, okay? And they have some window, and they all have the same window. We assume that equally influences. And you end up with two camps. This is like two political parties. You're starting like this, the whole spectrum, then you end up with two camps, and these two camps do not talk to each other because they're too far apart. And that's what happens. So you can repeat this experiment. So again, this is a natural algorithm. It's an algorithm, and you want to be able to study it. You want to be able to make statements about it. You want to be able to make predictions. So what I want to argue is to do that, don't try to get some differential equation and solve it. It's going to be too difficult. Instead, design algorithms, which is different from simulation. I mean, you need simulation to make hypotheses, but ultimately to prove you need algorithms. Now, the final point I want to make is, until now we have assumed that the communication was bidirectional. That if I communicate with Adnan, and Adnan has a chance to communicate with me. Our phone is two-way. But often communication is not like that. When you listen to the radio, it's one way. You might want to talk back to the radio, but nobody's going to hear it. When the birds fly, the bird that's ahead does not see the bird in the back, whereas the bird in the back sees the bird ahead. So this is not two-way. So we have to be able to model things that two-way. And everything I've said so far was only for bidirectional. And bidirectional in the language of dynamical systems looks like this. The language would say that all of phase space is a basin of attraction, which means that any state of the system at any time is a point somewhere. And it evolves, but you've got those things, and eventually, one way or the other, it will end up at the bottom of one of these things. Now, you want to know whether that is still true when you have non-bidirectional, when you have one-way communication. What if I can influence you, but you cannot influence me? And the answer is yes. One-way communication changes everything. Okay? And I don't think intuition is obvious why that should be true. Okay? So, a world where you can only communicate by talking to each other is fundamentally bidirectional. Because I talk to you and you can talk back. Now, suppose there's a world which has both two-way communication, but also has radios and TVs and things where it's one way. Okay? This world is fundamentally different from the world with two. This is important to understand that. So I'll briefly tell you about it. I'll take the time to make sure I'm not. So I think I have like 5-10 minutes or something like that. Yes? Good. So these are called endogenous agreement systems. So it's the same setup, except now, here's what will happen. So let's say this is me, I, and this is Adnan, Jay, and now first of all, we will make this directed. And so at any time, there are 4 possibilities. Either there's no edge at all between us, there's one edge from me to him, or there's one edge from him to me, or there are 2 edges both ways. So there are 4 possibilities. Okay? Now how do we decide? Well, everybody will have their own selection criteria, and they could all be different. So I will have my own little logic where I see where everybody is currently sitting, and right now I will decide whether I want to be influenced by Adnan or not. I get to decide that. And he gets to decide if he wants to be influenced by me. The way I decide this with Adnan might be different with somebody else. So there is a logical formula which takes as input the entire configuration, the entire state of the world. And on that basis, we'll decide whether I communicate with Jay or not. Okay, and so in spite of ij, everybody has their own choice. I can choose what to do with any j. All right? And this is formulating the theory of the reals. I can rely technical about this. And it basically says such that any number, this can work forever if I want. And this is, you can do pretty much any criteria you want. Or I can have something very simple. I will communicate with Adnan if he's within 10 feet. That's fine too. Okay? So when you perform experiments, what do you get? Remember, in the previous examples, things always converge. But if you actually play, you see something very interesting, which is that sometimes it converges. Often it does, actually, but sometimes it does not. And you get something like this. And you say, well, maybe it'll stop at some point. But it never stops. So this would be a situation where, let's say to go back to the political example, it's not that society reaches a polarized state where everybody is divided up into, say, two camps. You've got the left wing and you've got the right wing, and that's it. This changes all the time. Think of musical chairs. It's like you will end up becoming right wing and left wing and right wing. They'll be constantly forever. You keep on changing forever. Okay? So this is totally unstable in that sense. I mean, how can that happen? So what I can show you is that not only it can change all the time, but it's periodic. You'll do so in a periodic way. So this is very strange. I will end up, after a while, I will end up moving in phase space along a trajectory which will be a loop. I just go and repeat my same sequence of opinions. So I would change opinions, 10 times. And then I go back to my original opinion. And then I will change 10 times again. The same sequence, always, forever. It's very strange. How is that possible? Now, dynamical systems people might say, well, this is obvious because the system is piecewise linear and therefore there must be some kind of pumping lemma there, and that's not true. In fact, piecewise linear systems are Turing universal. So you can have any behavior in this. So that's not satisfactory. Why it's periodic. Not to be technical, but at least maybe I don't know if it's periodic or not, but it cannot be chaotic. Because the so-called Lyapunov exponents are not positive. It is true, the Lyapunov exponents are not positive. But this does not imply it cannot be that. In fact, there are systems that have non-positive exponents that are chaotic. So that doesn't work either. So there are, the proof sketch has really two parts. And one of them is this concept of renormalization, which really comes from physics, statistical physics, the notion of renormalization group. But I can quickly explain this one. Now, suppose it is a fact that at any time, for any cut through the graph, so anywhere you draw a yellow line, there exists arrows going in both directions. Let's say that's true. See, in this case, there are arrows going in and some going out. Let's suppose that at any time, whenever you draw a cut in the graph, if you look at the flow of information, you see that there are flow in, out, and out, both. If that is the case, then this is very good, because then you can monitor the flow of information all across the system. And somehow, I won't tell you how, but somehow you can decompose the system into two parts. One that's so-called oblivious, and the other that's contracted. This means it's good. It's a very good thing that's happening. What if it's not true? What if at some time there is a cut and all the information flows in the same direction? Say it flows from the out to the in. Then that's bad. That's bad. So what do? So here's what you do. You wait until this ceases to be the case. So you just wait and you see whether it's true at the next step and the one after. And you wait until finally there's flow in both, which might never happen. You may have to wait to infinity, but that's okay. But if it's not infinity, then it's going to happen maybe in 2 years from now. What you do is you renormalize time where the basic unit now becomes 2 meters. So this is something that is done commonly in physics, but not in computer science. So anyway, that's what you do. And finally, you look at the bifurcation tree. It's a very beautiful thing. Now, when you are in phase space, so by phase space, I mean, you know, there's this collection of H's in here, say, 2 dimensions. So we think of ourselves as H's, and we have a position. But now think of all of us as one point in very high dimensional space. So think of space being, let's say there's 50 people here, and each one has 2 coordinates. So think of a 100-dimensional space, where now the configuration is 1 point. Okay? And now this point moves by the dynamics of the system. That's called phase space. Now, follow not just the motion of 1 point, but the motion of a whole ball around a point, and see what happens to it. Now, since the whole thing is piecewise linear system, the behavior within, there are cells like this, complex cells, and within each cell the behavior is the same. So what happens is everybody who is within this will be going to the same thing. So you follow this and say it falls here, and then say it falls there at the next step, and then it falls there at the next step. Now, if this moves like that forever, then it's easy to prove what I've just claimed. But unfortunately, it may not happen like this. What may happen is this. It falls in the middle. Now, if this happens, there's what's called a bifurcation, because the pulse here will be sent somewhere, but those on the other side are sent somewhere else. Okay? I mean, this is like somehow a group of people get stuck in the middle of a checkpoint with half of one side and the other one, and their fate might be different. So then they might end up being split and going into different direction. Now, if this happens again, then they will be split again. And if this happens again, then they will be split again and again and again and again. If ultimately this becomes so big it covers everything, then it cannot be periodic. So this cannot happen. Now, as luck would have it, the system is dissipated. I mean, if you had to have some kind of analogy, physical analogy to the system I'm describing, this would be springs. I mean, there's a point here and there's springs and they're pushing. These are influences. This spring, pulls me in this way and pulls me that way and pulls me that way. And such systems are called dissipative for all kinds of reasons. And because of that, you can see that actually the picture is not that, but it looks like this. It's a so-called Cantor-Sink, which means that it's an infinite number of dots, but some are big and some are small. But those that are small completely outnumber the big ones. And okay, so you may have seen like fractal pictures and things like that. Anyway, so this is my last slide and the moral of the whole story, which is, I mean, you might think, well, I don't know where the computer science here is, but I really want to draw your attention on the fact that I really believe I gave a talk that is 100% computer science, in the sense that I try to understand natural algorithms, and it's my belief. But to do that, we have to think algorithmically, and we have to come up with algorithms to understand, because that's a new language to understand those objects. Okay, thank you very much.
We have, say, 10 to 15 minutes of questions.
In natural algorithms, the algorithm is decided for us by nature. But when we have to model it, we have to write the code for the algorithm, and that we have to do ourselves. So when I draw this network around the birds, and I say, this bird looks at its friends, neighbors, and takes the average, that's what we humans think birds do, but birds don't tell us what they do. So first of all, we could be making a mistake, that we don't model the algorithm the proper way. That could be. And in fact, it's almost certainly true that we make mistakes. Things are much more complex than we say they are, which is why the bounds that I showed, which are exponential, I don't think should be valued for what they are. In other words, the fact that it's exponential to me is meaningless. It doesn't matter what it is. It could be polynomial, it could be exponential, it could be double exponential. What matters is that they are bounds. Because even when I say they're optimal, I'm not saying birds fly that way. I'm saying the model we use gives this behavior. But the model we use might not be what birds do. In reality, we know that birds converge very fast. Okay? Things are always much, much better. So in computer science theory, we always favor a worst case analysis. You said, what is the worst case possible that could happen?
Well, have you looked at the average case analysis? That's not possible.
Yes. So I think that's exactly the sort of thing that we should be doing. Now, as you know, average case analysis is usually much more difficult than worst case. And so I think that the methodology is this, that first we have to look at the worst case, simply to get our feet wet. And then once you start building tools, then you will say, well, what about the average? What do they do? And you will find that the numbers are much smaller and that the complexity is much, much lower. That's why I don't think one should pay attention to the actual bounds, but one should pay attention to the techniques that are used to put in the bound. And so the second thing is in practice. So the answer is absolutely yes. So at Princeton, I work a lot on birds because, well, in my university, it's one of the best places in the world to study flocks and herds of birds. There are at least 2 different departments where these people are very practical. I mean, they have birds and they have tanks of fish and they perform experiments. So they're on the total opposite side of me, and we try to meet halfway, where those people do really applied science. They measure actually, in seconds how long it takes for things to happen. And the big challenge really is, and they're not computer scientists at all. And the big challenge is how computer scientists can talk to these people and find a common language and ultimately work together. So I've begun to work with them, and I found it actually quite difficult, simply because the cultures are so different. And I certainly, they have no interest in this big O of 2 to the n. For them, it's like science fiction. And at the same time, from a scientific point of view, you feel what they're doing is just lots of measurements, and they produce lots of data. But they don't really do the kind of science that we'd like to see. So all this is still in its infancy, but I think that it's very important, though, to be talking to scientists who actually deal with these objects of natural algorithms, and who actually deal with the algorithms themselves, with birds and fish and people doing politics, and so on. And but among computer scientists, the answer is by and large no. I mean, there's been a lot of people doing natural algorithms for the internet, if you can call that a natural algorithm, which is debatable. But I think that, yeah, exactly, or distributed computing on large networks, and that's, so we can meet with those people. But I would personally want to reach out to biology, for example, and people doing protein interaction networks and so on. But as often in science, the most difficult is not so much the actual science, but is finding a common approach, common language, and this is very tough.
Okay. How can we use the natural logarithm to serve the political model, as you said,
So,
and make it applicable in the election, and make this party win the election other than the other party, or have more votes than the others? Yeah.
So actually, I've had students look at precisely this. Right now, what I've talked to you about is a free and fair system where everybody is entitled to interact with anybody else, and you're influenced by something. But consider a variant. here's a variant. Let's say there are 10,000 participants, there are 10,000 people in the system, and now you are allowed to introduce 100 fake agents that you pay to influence others. Where should you place them? Okay, so imagine that there's a certain number of players, and I want to force an outcome at the election, the ballot box, but I have a finite budget. I mean, I could overwhelm the system. If there are 10,000 people and I hire 200,000 people, then of course I can predict anything I want. So, but let's say I cannot afford it. Say you're a political party, but you're not that rich, and say there are maybe even 1 million voters, and you can only get campaign help. So let's say that you get 200 people. How should you place them? How should you plan to use them to influence others? Okay, and now this is so. I have students look at this, but this has been studied in the context of viruses. Okay, actually, there's a case in the U.S. not long ago where every year there's an epidemic flu, and the track where it propagates. So this is like this network. It propagates through communication, and then there was a shortage of vaccines. So let's say that you have a small number of vaccines, much smaller than the population that could be exposed. Then the question is, who should you give those things to first? So what they decided was that you should target certain metropolitan areas and go to the hospitals and give it to the nurses. Actually, the nurses were the most important, that they should get because if they get sick, they're most likely to spread to others. In hospitals, people are weaker because the immune system is down, so they're more likely to get sick, and so on. So that's the kind of reverse. It's the same problem, but in reverse, right? If you want to influence the election, you want your ideas to spread. Here, it's how to stop the spread of an epidemic when you have a finite budget. So yeah, there are a lot of people thinking along these lines, and for the better or the worse. I mean, I think it's
I actually, it's difficult for me to understand why they are natural algorithms. I mean, they were, because I see you try to model very, very complex situations, like movements of pairs, or for example, elections, or political regimes, but always modeling such complex cases, we always look to certain parameters and we forget the others, because we cannot account for everything, and which usually leads to not to really to answer the goals we want to have, which vaccine we want to give, or what the political opinions change, and so on. So is there a work on how do you model natural cases using for these algorithms?
So this is a very, very good question. This is a very, very good point. But first of all, let me start my answer by saying that this problem is not new to this. This is true in physics. Actually, the previous talk by Cédric Villani I heard before talked exactly about this, how Newton's equation allows you to model all the galaxies and all the planets and everything. This is totally beyond our ability to handle. So then we end up making all these enormous simplifications and assumptions. And now the question is, so now we have actually a mathematics of celestial bodies that is completely false, because we've dropped the influence of all sorts of things. And as he said, when we drop these things, we have no idea whether, I mean, we think our intuition tells us that it's okay to ignore this and to ignore that, but actually it's faith. Actually, we don't know. We cannot prove that it's okay to drop those things. So even in the sciences, we very often make, people always think that, religion is faith and it's totally subjective, and science is totally objective. But that's not true at all. In science, there's a lot of subjectivity where sometimes you decide to simplify, but you have no rationale for simplifying. It just feels that way. But in fact, it's impossible to, you hope for the best. And there's a lot of that. All these models that I described, for the birds, I'll tell you how the model was, and this is also a big mystery, actually. In computer graphics, so there's some of you who must be doing computer graphics, right? But the whole field of computer graphics, you know, I remember because I'm old enough to remember when the field was created, but to produce an apple that looks like an apple took like 30 years and was considered a major area of, or a banana, or just a realistic fruit that would be a computer graphics representation. Involved enormous research in optics, in reflection, in refraction, in color representations, in 3D things. It's very complex. And finally, after years and years and years, we got something that kind of looks like a picture of an apple. So that's good. But here's what happened for the birds. And this is really phenomenal. There's this guy, Reynolds, who is playing with virtual reality kind of objects. And he wanted to build points, I mean, little creatures that look like birds, and he wanted them to fly and look visually like birds. And he came up with these rules. And then he simulated them on a computer. And what he saw, actually I have some video, but I didn't have time to show them to you. They were completely amazing. I mean, within 48 hours, he thought about it, and then he wrote the code, and then he looked at it, and he said, oh my God, these are so good. They're very hard to distinguish from real birds. So exactly the opposite of an apple. An apple took 30 years, and in Hollywood today, every movie that has more than 5 birds, these are fake birds. And most people cannot tell. In fact, they've been tested where they're real birds and fake birds, and you have like 30 seconds to look at it, because otherwise you can tell. And people basically, it's 50-50, they don't know. And so here's the question, actually, which is, why is it so easy to simulate the flight of birds? I mean, and why are apples so difficult? Why is it that for apples it took 30 years, and for birds you have these simple rules, and the result is visually, maybe not scientifically, right? Maybe if birds looked at it, they would say, "Oh my God, you're crazy! These are not birds." But for us, so that also, I think, is an interesting scientific question, because maybe it says something very profound about the way birds fly, that we can simulate it very simply. And so, yeah, that's
so, I mean, you come to the point is that in open worlds, I see the complexity. So the question then, is there are some closed worlds where these kind of natural algorithms, what's called natural algorithms, could really help in life?
So,
because in closed worlds, the parameters are deterministic, right?
Yes.
And then we can maybe find an advantage or an application for these algorithms. Is there a closed world application for this?
So I don't think there's such thing as a closed world, but maybe sometimes you can pretend there is and it works well. So for example, there's been work, I've done some work on annotating proteins. So we have all these proteins, and we basically don't know what they do. I mean, proteins have functions. Some carry oxygen, some do things. And we'd like to know what they actually do, and we don't. So people build these networks of interaction, very similar to what I say, of proteins interacting. And then if a protein interacts with another protein, that then will be sharing similar functions. And then they try that to make these predictions, and then they can test the prediction in the lab. Now, if this is true, if this worked, and this might well work, the consequences for the pharmaceutical industry would be huge. And that would be really, really huge, because it's very hard to, pharmaceuticals right now have not produced any great breakthrough medication for many years, so they're really desperate for something. Yeah.
Just First, I would like to come to the point of trust. You mentioned the point of trust as key element in the whole process.
Yes.
And I wonder about the experiment that you conducted about trust, and you come up with two parties.
Yes.
Which means that this is really justifying in our life the political situation that always we have two things. This could be one of the justifications for that or not. This is one thing.
No, yes, I think yes. I mean, I believe that yes. Why there always are two things,
Yeah, this
and
is-
first is built. Yeah.
Yeah.
But something else which is very important also for stability, and I didn't mention this, is self-confidence.
Yeah.
That if you remove self-confidence, and let's say that regardless of trust, let's say that you're influenced by your friends, but you always ignore your current opinion. Let's say you do that because you don't trust yourself. And suppose that's true of everybody, and the system will never stabilize. And that, I was talking to an educator with children, and I told them that, and at first they were surprised, but then they said, but you know, I think I understand what you're saying, because there's this paradox, okay, that children who have no self-confidence and therefore are willing to follow the teacher, anything the teacher says, you would think they would learn faster, and the community would get, you would think the community would get together more quickly if nobody believes in themselves, because they simply listen to the other and they just do what the other wants. But that's not true. She observed that in fact, the community becomes very, like, periodic, it changes. And when the child has, now you don't want to be stubborn. The child who simply refuses to do anything besides their own opinion is a nightmare, then nothing new. But it's very important that a child should maintain, you know, he's not going to be swayed over by a friend. So if a friend says, try this new food, you know, the child will really think twice about it because maybe it's dangerous and will kind of use their own self-confidence. And so that I think trust, but also self-confidence, I think is very important.
Yeah. And I think the issue of social media now, and for example, if we'd like just also to talk about politics and the concept of these movements that come directly to Egypt and Tunisia and the whole stuff, then this agent should come to the process, and how this agent could be analyzed, I think, is the key.
Yes.
If you'd like to understand these phenomena, why did it come at this point, and what are the parameters that could affect the process?
Yes.
This,
No, this is fascinating. Yes, yeah, like
Yeah.
a phase transition when you have all of a sudden.
and I think maybe if we reflect this into computing, then we will see in the future different, rather than Google, we will see other things that could come up with other stuff that could deal with these parameters once we understand these things more.
Yeah. Like for example, in the case of say Egypt, maybe one could have looked at, let's say somebody could have looked at all the Facebook and Twitter transcript, say 2 months before, and made a prediction that something big was going to happen. Maybe not, but we don't know. It's like earthquakes. I mean, I don't know, if you had a very precise transcript of the previous, you know, of all the seismic things, some people might be able. In the case of earthquakes, the problem is that we don't have the data because it's very hard to dig 100 miles underground. But now we have the data, so it's not unthinkable. I don't know how to do it, but it's not unthinkable that actually one could look at all these things and say. But the problem is it could work both ways because the government could look at it, and right and say Mubarak could have looked at that earlier and said, oh man, this was very good, so we have to have a preemptive strike. So yeah, it can be used both ways. But these are really very interesting questions. Yeah. And, very good topic.
Okay.
Thank you.
Thank you very much. شكرا لكم جميعا على المحاضرة. Always Professor Chazelle is welcome at anytime.
Thank you very much. I love coming here. I'll be back.
Next time, bring example from his book, maybe with mathematical
Next time he needs 2 hours for electoral politics.
Thank you very much for coming. It was great.